Okay, example number 4 says a 120, a 60, and a 40 ohm resistor are connected parallel to a 110 volt power source. We're being asked to draw a schematic diagram. We want to know what the equivalent resistance of the circuit is, what the current from the power source is, what the voltage drop across each resistor is, and then what the current through each resistor is. So when we draw our schematic diagram, there are kind of a couple of ways we can draw this one, but most of them involve really moving this one here or there. But other than that, it pretty much needs to look like this, okay? I guess the other way we could draw it would be like this. Right? Anything like that is going to be equal to this. I kind of like this way. If you guys like this way, that's fine. Doesn't matter to me. Okay. So I'm going to put 120 ohms. This one is 60 ohms. And I'm going to make this one my 40 ohm resistor. And this is my 110 volt power source. So what I have that's my schematic diagram. I want to know what the equivalent resistance of the circuit is. If we look back on the slides from earlier, we know that the equivalent resistance is equal to the inverse of the inverse of each of these, right? Okay. Do we want to put it in the calculator like that? No. Why not? Because we are going to have some problems because we're going to have to go ahead and make sure it's in the right mode, that blah, 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 blah. The easiest way to put it in the calculator is like this. 120 to the negative 1 plus 60 to the negative 1 plus 40 to the negative 1. Slap some parentheses around there. To the negative 1, right? And I have not calculated this out yet. Here is my calculator. I'm going to plug that in. 120, nope. Put some parentheses, 120 to the negative 1, plus 60 to the negative 1, plus 40 to the negative 1, to the negative 1, right? And that gives us 20 ohms. That is my equivalent resistance, 20 ohms, all right? So part C, that's B, says, what is the current from the power source? If I want to know what the current from the power source is, and I know my power source is putting out 110 volts, then I'm going to say V equals I times R. I'm going to go ahead and say VAB equals I times RT, and I know that that current is the current coming out of the battery, right? So VA to B is 110 volts. 110 volts is equal to I times 20 ohms, which means that my current is equal to 110 over 20, which is going to give me what, 5.5? Yep, 5.5. So that's 5.5 amps coming out of the battery. I'm going to go ahead and label that here, 5.5 amps, and I'm going to say RT equals 20 ohms. Now, it says what is the voltage drop across each resistor, and then it asks for the current through each resistor. So, interesting thing to note on this is that if we want to know the voltage drop across each resistor, and we look at our circuit diagram, we know that the voltage drop across each of those resistors is exactly the same as the voltage drop across every other resistor that it's in parallel with, right? Only because there is only one resistor in each leg of the circuit here, okay? If I had two resistors in series inside one of these legs, then I would have to modify my arrangement as far as my voltage is concerned. But as long as it's like this, and there's only one resistor here or one resistor in each leg here, I know that my voltage from A to B is the same whether I measure it from here to here or from here to here, right? Or for that matter, any one of these points across from the top to the bottom in between them. So for D, the voltage drop, and I'm not even going to bother putting it down here, I'm going to put it up here, is 110 volts. 110 volts. 110 volts. All right? That way we have it associated with each resistor. All right. Now, what is the current through each resistor? This is the part, it's not tricky at all, but this is the part that you actually have to calculate stuff and then add some things up for. So if we want to know the voltage, the current through each resistor, we're going to say V equals IR, and we're going to apply Ohm's law to each individual resistor. Well, to apply Ohm's law to each individual resistor, we have voltage, yes. We have resistance, yes. We can find current. Do we have voltage? Yes. Do we have resistance? Yes. Then we can find current. Again, same thing, right? So for the first one, I'm going to say V is 110 volts. 110 volts is equal to I1 times 120 ohms, right? So 110 volts divided by 120 ohms gives me 0.92. So I1 is equal to 0.92 amps, right? I could say 0.916 amps if I really wanted to. There we go. I'm off the page there. But it doesn't really matter to me too much which one. I would accept either one. For current 2, we're going to say voltage is still 110 volts. 110 volts equals I2 times resistance 2 is 60 ohms times 60 ohms to find I2. We're going to say 110 divided by 60. And that gives us 1.83 repeating. 1.83 amps. Make sure that does not get confused with an extra 1. 1.3 amps, right? The last one here is current 3. So we're going to say I3 equals 110 volts divided by 40 ohms. And that gives us 2.75. All right, now I want you guys to notice something. When we're looking at this, we have I3 is 2.75 amps. This is 1.83. And then this is 5.5. Nope, that's there we go. 0.92 amps. Okay. So when we look at our circuit diagram here, what we should pick up on is this is 120 ohms, 110 volts, 0.92 amps. 60 ohms, 110 volts, 1.83 amps. 40 ohms, 110 volts, 2.75 amps. Okay. The lower the resistance, this is 40 ohms of resistance, and it has a higher current passing through it. This one is the middle resistance, right? And it has the middle current passing through it. This one is the highest resistance, so it has the lowest current. Current is the amount of charge passing through a certain point over a certain amount of time. So it's expected that we're going to have fewer electrons passing through the area of higher resistance. Okay, it's like cars going down the road. If you have an area with a bunch of stoplights, you're going to get fewer cars passing through that area if it's easier to take a parallel road and get to the same place. Okay, notice that if we add all of these up, we also get 5.5 amps as well.